Hello everyone, my name is Chenda and I'm very happy to present this work, a new way to achieve round-efficient Byzantine agreement protocols. And this is joint work with Matthias Fitzi and Julian Loss. So let's start by recalling the classical problem of Byzantine agreement, which is a fundamental building block in the construction of many distributed protocols. So here we have a set of parties connected via some communication network, typically a complete network of point-to-point authenticated and synchronous channels. And each party holds an initial input xi, and the goal of the protocol is to reach agreement on a common value y. And moreover, it is required that if all honest parties start with the same input x, this is what they all output. And of course, these two properties must hold even when some of the parties arbitrarily misbehave during the protocol execution. And in this work, we consider active corruption, right? And the adversary is moreover adaptive. This means that it can adaptively corrupt parties at any point in the protocol. And in fact, it will be strongly rushing in the sense that it can take back any message that was not delivered yet from a corrupted party. So a crucial efficiency metric in Byzantine agreement protocols is the round complexity. That is, how many synchronous rounds of communication do we need to reach agreement? And from the early work, the very early work of Dolev and Strong, we know that it is possible to achieve agreement with a deterministic protocol within t+1 rounds, where t is the corruption threshold, and that this is actually optimal for deterministic protocols. And we also know that if we use randomization, we can actually do much better. And here we usually distinguish two types of randomized protocols depending on the termination flavor. So the first type are what we call fixed round protocols, and these are Monte Carlo style. This means that they are run for a fixed number of rounds, but they are allowed to fail with a small probability, which typically is negligible in the security parameter. And in this regime, the most efficient protocols, assuming a one-round ideal coin flip, are due to Feldman-Micali in the t smaller than n3 setting, and by Micali and Vaikuntanathan in the n½ setting. And both protocols achieve an error of 2 to the minus r when run for 2r rounds. The second type of protocols that are considered in the literature are those with probabilistic termination. And these are Las Vegas style. This means that they are guaranteed to reach agreement with probability 1, but there are some executions that take forever. And on the other hand, in this mode, the advantage is that one can achieve protocols that run in a constant number of rounds in expectation. But an important feature that fixed round protocols achieve compared to those that are with probabilistic termination is that the former achieve the so-called simultaneous termination. This means that all honest parties terminate at the same time. And this is particularly useful when using such protocols as building blocks in larger applications. And although our techniques also lead to improvements in the probabilistic termination case, in this work we focus mainly on improvements for fixed round protocols. So the typical approach to achieve round efficient BA is by following the so-called Feldman-Micali paradigm. And this paradigm was introduced already 3 decades ago and is the basis of many round efficient BA protocols. And the idea here is that there is a number of iterations, which for the purpose of this talk, we will think that is fixed. And each iteration consists of 3 components. First, an execution of a weaker type of agreement is invoked, which I call it weak consensus, although originally it was referred to as Crusader's agreement. And this primitive achieves a weak form of agreement. And the idea is that, let's say, parties start with an input bit, and then they output either a bit or bottom. And there are two guarantees. So if all honest parties start with the same bit, they keep it. And moreover, there cannot be two honest parties that output different bits. It can be that some honest parties output a bit B and others bottom, but not contradicting bits. So in the second step, parties execute a coin flip protocol that allows them to obtain a common random bit C. And finally, if bottom was obtained as output of weak consensus, then the party takes the value of the coin. And then we repeat this process enough times. So the effect here is as follows. So if at any iteration all honest parties start with the same input X, then they will also output X at the end of the iteration. And this is because the output of weak consensus by the first property will be X as well. And because this is a bit, no honest party will adopt the value of the coin. And therefore, once agreement is reached, this will be preserved until the end of the protocol. On the other hand, if parties start in disagreement, then one can see that with probability 1/2, they will be in agreement at the end of the iteration. And this is because at the end of weak consensus, the output of the parties lie within B or bottom. And if the coin hits the value B, then parties will be in agreement. And therefore, after k iterations, agreement is reached except with probability 1/2 to the k. And an important point here is that the coin value and the output of weak consensus must be independent, in the sense that if the output of weak consensus can depend on the coin, then this doesn't work. And therefore, intuitively, with this approach, one needs at least 2 rounds per iteration, one to start the weak consensus and the other one for the coin that needs to start later, right? And this is exactly what current protocols achieve when assuming an ideal 1-round coin flip. Kind of 2 R rounds for agreement with probability 1 minus 2 to the R. And our contribution is a new way to achieve these BA protocols, and this will be actually a generalization of the Feldman-Micali paradigm, which we refer to as expand and extract. And this new way to achieve BA protocols supersedes many of the previous designs, and at the same time allows to improve the round efficiency of BA protocols. And in this generalization, we also have 3 steps. But the first step is what we call an expansion step, where we invoke a so-called proc-census protocol. And here the idea is that we increase the domain to size S. At the start, let's say that the parties start with an input bit, and the output now is a domain of size S. And note that in the Feldman-Micali paradigm that I just described, the domain was of size 3. And pictorially, one can view this as each party outputting one of S slots in an array with 2 guarantees. The first is that if all honest parties have input 0, then all honest parties output the leftmost slot, which I marked in green. And if all honest parties input 1, the output is the rightmost slot. And the second guarantee is that the honest parties' outputs lie within 2 consecutive slots. So it can be these 2 slots, or those 2 slots, or any 2 slots, but they need to be consecutive. So the second step of the iteration is also a coin toss protocol, but here the coin will take a value, which is in the domain of size s-1. And then the third step is an extraction technique, which given the information of expand and the coin, it will extract an output bit. And the extraction technique that we use here in the paper is simply a cut. So we view the s-1 possible places where we can cut the array, and we simply cut at the position that the coin indicates. Then the side where the party lies after the expand step indicates the output bit. So for example, if c equals 3, then if the output of expand was at the left of the coin, then the output of the iteration is decided to be 0. And if it was at the right, then the output is 1. And the point here is that because honest parties lie within 2 consecutive slots, they will reach agreement unless the cut exactly splits the honest parties. And therefore, the agreement now is essentially 1 over, the agreement probability will now be essentially 1 over the number of slots. And by adjusting and coming up with protocols for the expand step, so consensus protocols with different number of slots, we will be able to optimize the agreement probability and improve the round efficiency. So with this new design, we give improvements in the setting of protocols assuming a one-round ideal coin flip, which can be instantiated with a trusted setup of unique threshold signatures, and where security is proven in the random oracle model. So one of the results that we show in the paper is that actually one can obtain an exponential number of slots in R rounds, so 2 to the R slots in R rounds, when up to a third of the parties is corrupted. And with this, we can in fact achieve agreement within one single generalized expand and extract iteration. And as a result, the protocol is also twice as the best previous protocol in this setting due to Feldman and Micali. And the second result that we show is that with this paradigm, we can also achieve an improvement of 1 over 4 over the state of the art, which in this setting, which corresponds to the protocol due to Micali and Vaikuntanathan. And in the remainder of the talk, I will describe the first result. So the core of the protocol is an expansion technique that achieves an exponential number of slots in the number of rounds. And here the idea is that we design an information theoretic compiler that transforms any consensus protocol with S slots into one with 2 times S minus 1 slots in one additional round. And the protocol is better understood with an example. So let's say that we start from prox5. This is a consensus protocol with 5 slots. And this is actually the first step of the compiler. Parties run prox5. And at the end of prox5, each party outputs one of these 5 slots, and then echoes the slot to all other parties. And then all parties make this output determination to choose or to decide which of the 9 slots they will output. So the range goes from 5 to 2 times 5 minus 1, which is 9. So I depicted here the consensus with 9 slots vertically, and now I will describe the conditions to output each of the 9 slots. So after the echo step, each party will receive a number of votes on each of the slots. And I indicate in red the region that indicates that the party receives n minus t votes. So that is for the first slot. We require that the party receives n minus t echo votes on the leftmost slot of prox5. And observe that this condition is the condition that is guaranteed when parties have pre-agreement on 0. And this is because if parties have pre-agreement on 0, then all honest parties output the leftmost slot in prox5. they echo this slot, and therefore all honest parties are guaranteed to receive n-t votes on this slot and satisfy this condition. And the idea is that the following slots are derived in such a way that if an honest party satisfies kind of the previous condition, then all honest parties satisfy at least the next condition. So more concretely, let's see what happens with the second slot. So here we will require that there are n-t votes on the red region, and n-2t votes lie on the left part of the region. And note that the idea is that if an honest party satisfied the first condition, that is, it received n-t votes on the leftmost slot of prox5, then it is guaranteed that all honest parties receive n-t votes in the red region, because they lie within 2 consecutive slots. And moreover, from this n-t, there were n-2t parties that were honest. So therefore, all honest parties are guaranteed to receive at least n-2t votes on the leftmost slot. And now with a similar logic, we can derive the condition for the third slot. And here what we require is that the parties obtain n-t votes in the red region, just as before, except that now we require the n-2t votes to be on the right side of the red region. And the effect here is that if there is an honest party that satisfies the second condition and no honest party satisfies the first, then all honest parties satisfy either the second or the third condition. And observe that this comes from the fact that if an honest party satisfies the second condition, this means that there was an honest party that echoed a vote on the leftmost slot, because n-2t is larger than t. And therefore, the votes from honest parties all will lie within the red region. And then if you have n-t votes, then either you have n-2t on the left or on the right. And with a similar reasoning, we can derive the fourth condition, and this is derived in such a way that if an honest party satisfies the condition 3 and no honest party satisfy neither conditions 1 or 2, then it is implied that all honest parties satisfy conditions 3 or 4. And this is kind of the logic how we derive this condition, right? So to summarize, the idea was we invoke prox5, we echo the slot of prox5 to everyone, and then output the most extremal slot that satisfies the corresponding condition. And we derive the condition starting from the extremal slots in such a way that it is ensured that if an honest party outputs some condition, then all honest parties satisfy at least the next condition towards the middle slot. And moreover, the conditions are designed in such a way that they do not overlap, in the sense that if an honest party satisfies a condition in the upper half, so in the first 4 slot, then there is no honest party that satisfies a condition in the lower half slot. And with this approach, and starting from the case where the initial input can be interpreted as a slot in prox2, we achieve 2 to the r plus 1 slots in r rounds. And what is the effect of this? If we instantiate the expand step with this exponential proxensus protocol, what we will achieve is a protocol that runs in r plus 1 rounds and achieves agreement except with probability 1 over 2 to the r, which is what we wanted. So to conclude, the main takeaway message is that we give a new way to achieve PA protocols. And in particular, we show that the number of slots plays a crucial role in the round efficiency of PA protocols. So thanks everyone for listening, and here is a full version of the paper.